All right. So we will start off with our last chapter, unit wise. Okay. So it's the last unit. Okay. So the last unit is on power amplifiers. Okay. So the last couple of sessions we had discussed about power devices, okay, especially the thyristors. Okay. The important thyristors which we discussed were silicon control rectifier, diac, triac and unijunction transistor. Okay. So this unit is focused on the power amplifiers. Okay. So whenever we say power amplifiers, in most of the cases either we may use BJT or sometimes we may also use the power devices, which are the core active devices, so that the power amplifiers can be constructed. Okay. So let us just go through some of the basic aspects which are needed for us to understand with respect to the power amplifiers. Okay. All right. So some important points regarding the power amplifiers. Before we just discuss the different types of power amplifiers, before that I think it will be good for us to understand a multi-stage amplifier, okay, with an example. So this particular diagram shows us the microphone which is at the left hand side, and at the right hand side we have a speaker. We have a speaker. Okay. So the microphone acts as the input side and the speaker acts as the output device. Okay. Now in between we have the communication phase, right? Okay. The signal should get transmitted from one end to the other end, or to be specific, it has to be transmitted and then travel through the channel, and then finally a signal should arrive at the output side or at the receiver side. Now there are various stages of amplifiers that are used in different stages, okay, of an amplifier. At the input side, normally we use small signal amplifiers. Small signal amplifiers, because the power strength requirements will be very small, usually at the input side. So these are all small signal amplifiers. Okay. However, at the output side, especially wherein there is a requirement for high output power, we usually go for high power amplifiers. Okay. So here you can very clearly observe that there is a high power amplifier which is being used at the output stage, and these are large signal amplifiers. These are large signal amplifiers. Okay. So the point is, the communication systems make use of small signal amplifiers also, they also make use of large signal amplifiers. Okay. So both are very much necessary for us. All right. So the diagram which is being represented here is that of a communication system itself. It's a simple communication system. It could be a wired or it could be a wireless system, but the point is it's a communication system, right? So at the left hand side, microphone acts as an input device, okay, wherein the sound waves will be our input signals. And at the output side, the same sound wave, it has to travel through so many stages. While traveling through so many amplifier stages, there may be a probability that noise may interfere. There may be a probability that after each and every successive stages, the amplifier strength may reduce, right? Okay, while traveling. So it is the duty of these intermediate amplifiers to strengthen, okay, the signal, so that at the output side we get a large amplified high power output signal. Okay, fine. All right. So, some important points are that basically for the power in the communication systems, especially at the output side, we make use of large signal amplifiers. These large signal amplifiers are capable of delivering large voltage or current swing. Okay. So, try to focus on these words: large voltage or current swing, okay, or appreciable amount of power. Further, the main features of a large signal amplifier are the circuit's power efficiency, the maximum amount of power that the circuit is capable of handling, and the impedance matching. So, these three terms are extremely important that actually characterize a large signal amplifier. Okay. So, the first one is circuit's power efficiency. Okay, please note it. Efficiency is a very important terminology. Higher the efficiency, better is the power amplifier. Okay. Then the maximum amount of power that a circuit is capable of handling, and finally the impedance matching. Okay. All right. So, let us just try to differentiate between a small signal and a large signal amplifier. Okay. Because these terminologies help us a lot in understanding different classes of the power amplifiers, right, which we are going to discuss in the coming slides. Okay. But for that we will have to understand the basic difference, the primary differences between small and a large signal amplifier. All right. So, about a small signal amplifier, the peak to peak swing. Okay. So, what do we mean by the peak to peak swing? Say for example, I hope all of you know about how to fix an operating point, especially with respect to the DC biasing. Okay, we have learnt it, right? How to locate the Q point, right? And then how to draw the corresponding output signals. Okay. See, for example, in the diagram which is shown here, okay, for a particular input signal, there is a complete swing in the output signal. I repeat, the output signal is in complete swing with respect to the input signal. What does that mean? That means for any value of the input signal, there is an output signal. I repeat, what do we mean by 100% output swing? 100% output swing means for any value of the input signal, there is an output signal. Okay. That means I can call it as 100% output swing. Okay. So, whether this 100% output swing, is it present in the case of small signal or large signal amplifiers? Okay. So, let us try to understand. So, for small signal amplifiers, the peak to peak swing in the collector current is less than 10%, a very important point. Okay. That means there is no 100% swing happening in the case of small signal amplifiers. Okay. So, there is the output swing is less than 10% of the quiescent collector current, whereas in a large signal amplifier, the peak to peak signal uses all or most of the load line. Okay. So, you can just observe that, see, this is the characteristics of a large signal amplifier, it is not of a small signal, right. So, you can very clearly observe that for the entire load line, the entire load line has been utilized, so that the output signal is obtained for 100% swing of the input signal. Okay. So, that is the main point involved. Next, the output power in small signal amplifier is in milliwatts. Okay. So, for small signal, the output power is in milliwatts, or it is up to 1 watt, approximately 1 watt. Whereas in large signal or in power amplifiers, the output power is almost tens of watts. It could be 10, 20, 30, sometimes it could be even hundreds of watts also. Okay. Because of which we call them as high power amplifiers, right. Then, Small signal transistors are typically used at front end systems, a very important point, whereas where the signal power is low, whereas the power transistors are used near the end of the system, okay, any communication system, because the signal power and the current are high. Okay. See, this is obviously evident from this particular diagram, right? It's a communication system, right? So this is front end, right? So at the front end, usually small signal amplifiers are used because the requirement is of lesser power, whereas at the output side, right, we need large signal amplifiers. Further, in small signal amplifiers, transistor behaves linearly. Please focus on this word. In small signal amplifiers, transistor behaves linearly as the input signal variation is small, whereas in large signal amplifiers, the input and output current relationship becomes non-linear. Okay. So in most of the power amplifiers, the input and output relationship is non-linear. Only if the swing is completely 100%, then we can say that it is linear. Otherwise, they are non-linear. Okay, as the output signal swing is large enough. So with these basic points, okay, the differentiation between small and large signal amplifiers and this particular block diagram, let us try to differentiate, or let us try to understand the different types of power amplifiers that do exist. Okay. Generally, we differentiate the power amplifiers in terms of classes, a terminology called class. Okay. So what all terms are important in this particular class, right? In this particular class, the points that we focus on is the efficiency, okay, of that particular amplifier, okay, because it all varies with the amount of efficiency that a particular amplifier belongs to a particular class. Okay, so efficiency is a very important term. Then comes the output swing, okay, with respect to the input swing, right? And then the location of Q point with respect to the DC biasing of that particular power amplifier. So all these three parameters determine the class. Okay, all right. So based on these three things, let us try to understand. So first of all, how many classes do we have? I'll just write it here. We have 5 classes. Okay, the first one is class A amplifier, the second one is class B, the third one is class AB, the fourth one is class C amplifier, and the final one is called class D amplifier. Okay, so we differentiate the power amplifiers in these 5 different classes. Okay, so what are the features of these 5 classes with respect to efficiency, output swing and location of the Q point? Let's try to understand. So based on the location of Q point, right, I hope all of you know what a Q point is, right? Okay, yes or no? You know, say for example, a transistor's output characteristics coincides with the load line at a particular point. So that point of intersection is called quiescent point. If some of you do not remember, I'll just draw it like if you just feel that this is the output characteristics of any particular BJT and then the load line. Okay, so this point of intersection is called as Q point. Okay, fine. So based on the location of the Q point, we try to differentiate the amplifiers in different classes. So a class A amplifier has its Q point at the center of the active region. at the center of the active region. And what about its output swing? Its output swing is complete 360 degrees. What does that mean? Okay, that means if my output is, if my input is varying like this, then at the output side, okay, if you take, then at the output side there is output signal for each and every value of input signal. Okay, so that is the meaning of 360 degrees output swing. Okay, positive cycle 180 degrees, then negative cycle 180 degrees, altogether it is 360 degrees. Okay, so this value which is being mentioned in the bracket is the output swing. All right. Okay, so the Q point for class A amplifier is at the center of the active region. Just let me go to this particular diagram. So this particular diagram represents a class A amplifier, right? Because the Q point is exactly at the center and the output appears for each and every value of the input signal. Okay, fine. All right, so the corresponding collector current is also shown here, right? So you have a complete output collector current for class A power amplifier. Then coming to class B amplifier. For a class B amplifier, the Q point's location is at the cutoff region. Okay, you cannot precisely say that its position is here itself in the cutoff region, but we can very clearly say that Q point lies within the cutoff region. Okay, fine. Then what about the output swing? The output swing is only for 180 degrees. That means rest 180 degree of the input signal cannot be used for amplification. Okay, the output appears only for 180 degrees of the input signal, right? So you can just observe the output here, right? By the way, this is for class A output, this is for class B output. Then class AB, well, class AB is a mixture of class A and class B, right? So because of that, its location, the Q point location is slightly above the cutoff but not within the active region. Okay, it is slightly above the cutoff. What about its output swing? It is 180 degrees to 360 degrees in between. So a class AB amplifier possesses the characteristics which are in between that of class A and class B. Okay, and you can also observe the output swing here. Okay, right? So this is for, I'm sorry, it's not for class AB. Okay, it's not for class AB. This is for class C. Okay, fine. Then for class C, the location of the Q point is much below the cutoff region. And what about the output swing? The output swing is also much lesser than 180 degrees. Okay, so this is for class C. Usually class C power amplifiers are used in tuning circuits. Okay, and where do we use the tuning circuits? We use the tuning circuits in oscillators, LC tuners, right, which you have studied, the Colpitt's oscillator, the Hartley oscillators and all. Finally, class D amplifier, it's a special kind of power amplifier because here we try to convert analog input to its intermediate pulsed output. So the output here is in the form of pulses. Okay, so these are all digital pulses, and these digital pulses are finally converted back to their equivalent analog signal. Okay, so that is the purpose of class D amplifiers. Okay. So it is very clearly mentioned that class D amplifiers are used for pulsed operation. Okay. So that was a very brief distinction between different types of power amplifiers. Okay. Now what are the three parameters that affect the class of a power amplifier? The first one is efficiency. What do we mean by efficiency? How do we define efficiency? Okay. The power efficiency of an amplifier is defined as the ratio of AC output power to the DC input power. Okay, well, we all know about this particular formula, right? So efficiency is the ratio of output power by input DC power. Okay. So what does efficiency indicate? Efficiency indicates how well an amplifier converts the DC input power to AC output power. Okay, please focus on this. How well an amplifier converts DC input power to AC output power. Okay. So it is exactly the opposite of that of a rectifier, right? Rectification is AC to DC. Here the efficiency is all about DC input power to AC output power. All right. Then the next important parameter is power dissipation. So the amount of power dissipated by a particular transistor is the difference between DC input power and output power. Okay. So how do we define it in terms of expression? The power dissipation is DC input power minus the output power is a summation of DC output power plus AC output power. Okay, right? Because it's an RMS value, analog RMS value. So obviously it's a combination of DC output power plus AC output power. And finally, harmonic distortion. Okay, to some extent this harmonic distortion term is also important for power amplifiers. Okay, see, because the main intention of a power amplifier is to ensure that at the output side the power is increased, okay, or the output signal is of a very high power. In doing so, there may be a slight distortion in the frequency of the output signal. What does that mean? That means, say for example, if I have a power amplifier, okay, so that's a power amplifier, and to this particular power amplifier I am applying an input signal which is of 1 kilohertz, okay, and at the output side I want the same signal of a higher strength, okay, maybe a voltage amplifier, okay, for example, a high signal, a high power signal, but I want this particular output with the same frequency, 1 kilohertz. Okay, ideally this is fine, but practically it may not be so. Okay, at the output side we may get the signals which are of 2 kilohertz also, which may be of 3 kilohertz. Okay, so what does that mean? That means this 1 kilohertz original signal acts as fundamental frequency. Okay, so that is the fundamental frequency or the fundamental output that we actually want, but knowingly or unknowingly we may get other frequency signals also which are called as harmonics. Okay, now so with respect to application, harmonics may be good or sometimes they may be bad. It all goes with the application, end user application. Okay, so controlling the harmonics is itself a new thing, okay, in the power amplifiers. Okay, so the presence of harmonics of fundamental frequency at the output is called harmonic distortion, right? So you can just observe that if f is the original fundamental frequency, the second harmonic will be 2f, third harmonic 3f, fourth will be 4f. So in this way n number of harmonics may appear, okay, and sometimes they may have to be removed, sometimes they may have to be added. Okay, so all these parameters should be considered by circuit engineers when they are constructing good power amplifiers. Okay, all right. So I think we will stop here. Just a second. With respect to the classes, we have some more content, right? So you can just observe the waveforms. So these waveforms are from the textbooks. The theory contents you can just go through it later. Whatever points I had just explained previously, the same things are included in the slides. You can just refer it later. So that's the output for a class A. Okay, so that's for class B, right? Class AB, it is in between A and B. Class C, they are mainly used in tuning circuits, class C amplifiers. And finally the class D, they are used in pulsed operation. Okay, so just to differentiate, or just to perform a comparison of amplifier classes with respect to operating cycle. Operating cycle is nothing but, as I had told, the output swing, output signal swing. Okay, so for class A it is 360 degrees, right? The power efficiency, okay, just observe, class A amplifier's power efficiency is comparatively lesser, 25% to 50%. Okay, then class AB, okay, class B, the operating cycle is 180 degrees, efficiency is 78.5. What does that mean? In terms of power efficiency, class B amplifiers are better when compared to class A amplifiers. Okay, what about class AB? The output swing is 180 degrees to 360 degrees and the efficiency is between 25 to 78 point. Then class C, the output swing is less than 180 degrees. What about the efficiency? We are not talking about efficiency. Why? Yes, because we are interested, these class C amplifiers are particularly used in tuning circuit itself, wherein we focus on the resonance aspect, okay, the peak resonance. So for that purpose we are not interested in the efficiency of a class C amplifier, we are only interested in its tuning nature. Then finally class D, since it is pulsed based operation, okay, and its efficiency is typically over 90%. So in terms of efficiency, class D amplifiers are much better, and the reason is because of the pulsed operation or the digital nature of the signal. Okay, all right. So I think we will stop here. In the next class we will try to discuss each and every individual class of power amplifiers in a lot more detail. Okay, so just to summarize, what did we do today? We try to understand the concept of a power amplifier, where it is being used, especially in a communication system. What do we mean by a small signal amplifier and a large signal amplifier? What are the differences? And then we also discuss the different types of power amplifiers with respect to their classes. So class A, B, AB, C and D. What are their important features? Okay, all right. So I think we'll stop here, students. Any doubts, please ask.